Hello everyone, welcome back to my YouTube channel. So for this week, I'm going to explain to you how you should answer test 1 questions. So altogether we have 4 different questions and each question have 2 sub-questions. So let's get started with the first one. Question number 1A. A bubble of helium gas has a volume of 0.650 milliliter near the bottom of a large aquarium where the pressure is 1.54 atm and temperature is 12 degrees Celsius. Predict the bubble's volume upon rising near the top where the pressure is 1.01 atm and 16 degrees Celsius. In order for you to answer this question, you need to use the combined gas law. In the combined gas law, the formula is P1 V1 divided by T1 is equivalent to P2 V2 divided by T2. But if you can see, when you look at the questions, so the unit of the pressure is indeed in atm, but the temperature for both are in degrees Celsius. So what you need to do is that you need to convert this degrees Celsius to Kelvin. And then for the volume, it stays in milliliter instead of liter. So you need to convert this one as well. So what we need to do now is plug in the value for initial pressure is equivalent to 1.54 atm and the volume is actually 0.650 milliliter. So we convert it to liter, it becomes 0.650 liter, and the temperature, the initial temperature is 12 degrees Celsius. So 12 plus 273, that is for the initial one. So we are going to plug in the other one. So the final temperature is actually 1.01 atm and the volume is the thing that you want to calculate, and the temperature is 16 degrees Celsius. So you need to convert this to Kelvin, so plus 273. So from here, you should be able to find your V2 is equivalent to 1.0050 liter. So this is the final answer for the first question. Alright, let's move on to question number 1B. A sample of nitrogen collected in laboratory occupies a volume of 725 milliliter at a pressure of 98386.575 Pascal. Determine the volume that the gas shall occupy at pressure of 1.40 atm, assuming the temperature remains constant. So for this question, we need to use a little bit different in terms of the formula. So we are going to use a formula of P1 V1 equivalent to P2 V2. But before that, we need to look at the question again. So in the question, it states here that the pressure is actually in Pascal instead of in atm and the volume is in milliliter. The other pressure is already in atm and that's well and good. So what you need to do is you need to convert the unit from Pascal to atm and from milliliter to liter. So the first thing that I'm going to do is to convert from Pascal to atm. So basically you have 98386.575. So you can press your calculator. This should be converted into atm and you should get 0.9710 atm. Same goes with your volume. It's 725 milliliter, so you need to divide by 1000, so you should get 0.7250 liter. Alright, all of these are the initial pressure and also initial volume. So you can plug in the formula here. So you should get 0.9710 times 0.7250 is equivalent to the final pressure is equivalent to 1.4 and V2 is the thing that you are going to calculate. So V2 is actually equivalent to 0.9710 times 0.7250 divided by 1.4, and you should be able to get the value for V2 is equivalent to 0.5028 liter. So this is the final answer for question number 1B. Question number 2A. An ideal gas with an initial pressure of 1.4 times 10 to the power of 5 atm and an initial volume of 500 cm3 expand isothermally to a volume of 2200 cm3. Calculate the total amount of thermal energy transferred in joule to the gas during the process. Alright, this is a rather straightforward question whereby you have been told that this reaction follows isothermal reaction. So from here, you need to know that in an isothermal reaction, the Q is actually equivalent to your W. So from here, you can have your W is actually equivalent to nRT ln final volume divided by initial volume. Right, but the problem is that you did not know what type of gas that is being used inside this particular reaction, because given to you is just an ideal gas. So we have a lot of ideal gas there, so it means that we can't use this part of the nRT. But if you can recall the ideal gas law, PV is actually equivalent to nRT. So what we are going to do is we are going to substitute this in here. So we shall get W is equivalent to PV ln V2 over V1. So which P and V are we going to use for the initial one? So it means that here is actually P1 V1 ln V2 over V1. So what we are going to do now is plug in all the values. So W is equivalent to the initial pressure. So the initial pressure here is 1.4 times 10 to the power of 5, and the initial volume is 500 centimeter cube. So 500 centimeter cube divided by 1000, because you want to convert it to liter. So ln the final volume, which is 2200, same goes, divided by 1000 to convert it to liter, and initial volume is 500 divided by 1000 as well to convert it to liter. So you shall get your W is equivalent to 7 times 10 to the power of 4 ln 2.2 divided by 0.5, and therefore you shall get your W equivalent to 1.0371 times 10 to the power of 5. But you need to make sure that you know what is the unit for this. This is actually in the unit of liter atmosphere. So in the question you were asked to convert it in joule. So how are you going to convert it? According to the theory, 1 liter atmosphere is equivalent to 101.3 joule. So since you have this much, so it means that this value you need to times 101.3. So you should get the final answer is 1.0506 times 10 to the power of 7 joule. So this is the final answer for question 2A. Let's move on to question number 2B. A 0.5 gram samples of ethanol is burned, raising the temperature of 250 gram of water from 10 degrees Celsius to 28 degrees Celsius. When 0.8 gram of butane is burned, the temperature of the same amount of water at identical initial temperature increases 30 degrees Celsius. Distinguish which fuel produced the most heat energy per mole of fuel burn, given that the specific heat capacity of water is equivalent to 4.184 joule per gram degree Celsius. In order for you to answer this type of question, you need to do two different things because the calculation should be done for both fuel. So first and foremost, I'm going to calculate for ethanol. So the formula that you can use is Q equivalent to MS delta T. So we are going to calculate for ethanol. Right, so the Q for ethanol is equivalent to, so the mass is not the mass of ethanol. Instead, you should calculate the mass of water. So the mass of water is 250 grams, and the S is given in the question, which is 4.184, and the temperature, final minus initial, the final temperature is 28, and the initial temperature is 10. So the Q for ethanol is actually equivalent to 1.8828 times 10 to the power of 4. So we are going to do the same thing for butane. So we are going to use the same formula, Q equivalent to MS delta T. The mass for water is 250, doesn't change, and the S is also 4.184. But what is T? See here, it states here that it increased 30 degrees Celsius with an identical initial temperature. So initially is 10, so increase 30, sorry. So it means that final temperature is 40, initial is 10. So you shall get your Q is equivalent to 3.1380 times 10 to the power of 4. That is for butane. So the next thing that you need to do is you need to calculate the number of mole for each fuel. So number of mole equivalent to mass over RMM. So we are going to do with the ethanol first. So the ethanol, the mass for the ethanol is 0.5, and then now we are going to calculate the RMM. So because you have 2 carbons, so 2 times 12.011 plus, and then you have 5 hydrogen, so 5 times 1.0079 plus, then you have oxygen, just one oxygen, so 15.9994 plus, last one you have hydrogen again, so 1.0079. So after you have calculated this, you should get the number of mole for your ethanol is actually equivalent to 1.0853 times 10 to the power of -2. That is the number of mole for your ethanol. Alright, now we are going to calculate the number of mole for the other fuel, which is the butane. So same goes, mass over RMM. So the mass for butane is 0.8. So for butane is quite simple, only have 4 carbon. So 4 times 12.011 plus you have 10 hydrogen, so 10 times 1.0079. So you should get the number of mole for butane is equivalent to 1.3764 times 10 to the power of -2. Alright, so you need to look at the question here. So it's the question asks you to identify which of the fuel produce most heat energy per mole. Alright, so what you need to do is that you need to calculate one by one for ethanol and also for butane. So for ethanol, for instance, is 1.0853 times 10 to the power of negative 2 mole. For each of these mole will have the value of Q equivalent to 1.8828 times 10 to the power of 4. Therefore, if you have 1 mole of ethanol, how much energy or Q that you will have? So 1.8828 times 10 to the power of 4 divided by 1.0853 times 10 to the power of negative 2. So you shall get, for each mole is equivalent to 1.7348 times 10 to the power of 6. So up next we are going to calculate for butane. So for each and every 1.3764 times 10 to the power of negative 2 mole of butane shall produce Q equivalent to 1.1380 times 10 to the power of 4. Therefore, if you want to know 1 mole of butane, how much energy is going to be produced, so 3.1380 times 10 to the power of 4 divided by 1.3764 times 10 to the power of negative 2. So you should get, for each mole of butane, you should get 2.2799 times 10 to the power of 6. So from the calculation that we have done, we can say that for ethanol, for each mole, so 1 mole of ethanol will have Q equivalent to 1.7348 times 10 to the power of 6, while for butane, for each mole, the Q shall be equivalent to 2.2799 times 10 to the power of 6. So definitely this one is bigger. So the answer for this question is that the butane actually will produce more heat energy as compared to ethanol. Right, let's move on to question number 3A. Predict the volume that 12.5 gram of carbon dioxide gas shall occupy at a temperature of 40 degrees Celsius and pressure of 1.20 atm. Alright, when you want to calculate the answer for this kind of question, the first thing that you need to do is you need to look at the question, whereby you are given the type of gas, which is carbon dioxide, and also the mass of the gas. So since you know the mass of the gas, means that you are able to calculate the number of mole. So the number of mole for carbon dioxide is equivalent to the mass over Rmm. From the question, the mass for carbon dioxide is actually 12.5, and the RMM for carbon dioxide is, so carbon is 12.001 plus, there's 2 oxygen here, so 2 times 15.9994. So you should get the number of mole for carbon dioxide is equivalent to 2.7273 times 10 to the power of negative 1. Alright, so after that, what you need to check is on the unit for everything else. So the pressure is already in atm, that's fine. So the temperature is 40 degrees Celsius. So you just have to convert this to Kelvin. So since we already know the number of mole for the carbon dioxide, so the best formula that you can employ to answer this question is the ideal gas law, which is PV equivalent to nRT. So the pressure given to you in the question, which is 1.2 atm, and the volume is the thing that you want to calculate. N is this value here, so which is 2.7273 times 10 to the power of negative 1, and your R is equivalent to 0.0821, and your T is actually this one, 40 degrees Celsius. So 40 plus 273. So from here you can get your V is equivalent to 7.0084 divided by 1.2. So you will get your V should be equivalent to 5.8404 liter. So this is the final answer for question number 3A. Let's move on to question number 3B. Calculate the ionic strength of solution containing 0.4 molar of NaCl and 0.4 molar of Na2CO3. So you were asked to calculate the ionic strength of this mixture. Alright, so the first thing that you need to do is you need to know how this substance dissociates. So the first thing is NaCl. So it's very familiar to everybody. I'm so sure about this. So Na plus Cl minus. So what about for Na2CO3? Okay, I am very certain that you know Na should be Na plus. And if you don't know what is CO3, what is the charge here, right? Because you need 2 Na. See, because you need 2 Na, definitely your CO3 must be 2 negatives. That is why you need 2 Na lingering around there. So these are the two main things that you need to know prior to calculating the ionic strength. Alright, in order for you to calculate the ionic strength, so you need to use this formula. The ionic strength is equivalent to half times the summation of the concentration and also the charge. Alright, so the first thing that we are going to look at is the sodium. So the concentration of the sodium times the charge of the sodium square, and then plus, and then we have this chlorine also. So we have the concentration of the chlorine and also times the charge of the chlorine plus we have another CO3 here, so the concentration of the CO3 times the charge of the CO3 square. Alright, so basically you just have to plug in the value here because the concentration of Na or the sodium is actually 0.4. So 0.4. So how many do you have here? So we have 2 and another one, right? So you have 3 times 3. So times the charge here is actually the charge for the sodium is positive 1 plus. Okay, chlorine, how many do you have? Only 1, and this is for the NaCl, so it means that the concentration is 0.4. so 0.4 times this one have square. Chlorine is also negative 1 square plus, now we have CO3, the concentration is the same 0.4 as well, and you only have 1 times the charge is actually negative 2 square, right? So half, this one you need to find the answer for this, which is 1.2 plus this one, because negative 1 square is just 1, so 0.4. Same goes with this one, so negative 2 square is equivalent to 4, so 0.4 times 4 equivalent to 1.6. So after you have calculated all of this, so you should get your ionic strength for the solution is equivalent to 1.6. So this is the final answer for question number 3B. Alright, we are now at question number 4a. The following equilibria was found to contain 3 moles of hydrogen iodide, 6 mole of hydrogen gas, and also 1 mole of iodine. So the equation is given to you, and the total pressure of the seal vessel was 2.85 atm, and you were asked to infer the gas equilibrium constant for this reaction. So given to you is the number of mole for each gases. So from the number of mole, you can actually calculate the partial pressure. So the first step that you can do to calculate the partial pressure is to calculate the mole fraction. So we are going to start with hydrogen iodide. So the mole fraction for hydrogen iodide is equivalent to the number of mole of the hydrogen iodide, which is 3, divided by the total number of mole. So 3 plus 6 plus 1. So it's equivalent to 3 divided by 10. So you get 0.3. Alright, in order for you to calculate the partial pressure for hydrogen iodide is the mole fraction times the total pressure. So the total pressure is given to you in the question, which is 2.85. So 2.85 is the total pressure times the mole fraction, which is 0.3. So the partial pressure for HI is equivalent to 0.9120. Alright, so what we need to do now is we need to do the same thing for the rest of the gases. So we are going to do the partial pressure for hydrogen gas. So the hydrogen gas is 6 divided by 10, equivalent to 0.6. So therefore 0.6 times the total pressure, 2.85. So you will get the partial pressure for hydrogen gas is 1.7100. Alright, moving on to the mole fraction for iodine. So equivalent to 1 divided by 10, equivalent to 0.1. Therefore this 0.1 times the total pressure, which is 2.85. So you shall get the partial pressure for iodine equivalent to 0.2850. Alright, so from this value you can actually calculate your gas equilibrium constant for this reaction. Alright, since we have already calculated the partial pressure of each gases, so what we need to do now is we need to look at the balance equation here prior to calculate the gas equilibrium constant. So the gas equilibrium constant, which is the Kp, is equivalent to whatever in the product divided by whatever in the reactant. So the partial pressure for the product, which is the partial pressure for H2, times the partial pressure for iodine divided by the partial pressure for Hi. So but you can see here you have 2 Hi here, so means that you need to do square. So now you just need to plug in the values. So the partial pressure for H2 is 1.7100. Partial pressure for I2 is 0.2850, and for the Hi is 0.9120. So this one you need to have square. So in other words, we can say that your Kp is equivalent to 0.4874 divided by 0.8317. Hence, you shall get your Kp is equivalent to 0.5860. So this is the final answer for question number 4a. Alright guys, we have reached the last question for test 1. Calculate the molality for CaNO3 if the boiling point of the solution is 103.7 degrees Celsius. So given that the molar boiling point elevation constant, the Kb, for the pure water is equivalent to 0.512 degrees Celsius per molar. So how are you going to do this? The first and foremost, you need to look at the dissociation of this compound. So the first thing that you need to do is you need to know how this compound given to you dissociate. So you have Ca and O3 2. So how do you think it will dissociate? Definitely it will cut into 2, so your Ca will be Ca2 plus NO3 minus. So because you have 2 here, so you have 2 and O3 over there. So from here you can actually calculate the value of I. So value of I, this is my -1 and also +2, right? But in order for you to calculate the I, you don't need to look at the positive or negative, so you just have to add 1 plus 2 equivalent to 3. So your I is equivalent to 3. So since you were given the molar boiling point elevation, so the Kb is given to you, means that you need to calculate the delta T boiling equivalent to Kb, which is the value that is given to you, the molality, and also the value of I. Alright, what else is given to you? So it states here that if the boiling point of the solution is 103.7, so it means that you know that pure water, the boiling point of pure water is actually 100 degrees Celsius. So given to you is the boiling point, the new boiling point is 103.7. So in order for you to find the difference, delta means difference, right? So 103.7 minus 100, which is the actual boiling point of water, should be equivalent to the value of Kb given to you in the question, which is 0.512. Molality is the thing that you want to calculate, and your I equivalent to 3. So from here you can get this one is 3.7 is equivalent to 1.536 molality. So therefore when you want to calculate the molality is equivalent to 3.7 divided by 1.536. Hence, your molality should be equivalent to 2.4089 molar. So this is the final answer for question 4B. Alright guys, so this is the end of this week's video. Thank you so much for watching this video. I hope this video helps you to understand more on how you should answer all the questions for test 1. Thank you very much for watching. Take care, stay safe, and see you again next week. Goodbye.